Let's talk about the effects of the number of terms on the series expansion and approximation. Okay, so generally, the more terms we have in a series expansion, the more accurate the approximation of the series to the actual value. Okay, so for example, let's say we have sine x, right? And then given from our MF26, we know that the expansion is x, okay? Let's do a quick reference to our MF26. You can get it from here. And we are referring to the sine x over here, okay? So sine x is equal to x minus x cubed 3 factorial. So x minus x cubed over 3 factorial plus x to the power 5 over 5 factorial minus, now if you were to continue this, there's a pattern. So, we increase the power by 2, and then we have 7 factorial. Okay, we also increase the denominator, the factorial, okay, by 2 each time, so on and so forth, right? So we can go up to, say, x to the power 9 factorial minus x to the power 11 over 11 factorial, and then so on and so forth. Okay, so let's just do one more. Okay, so 13 factorial plus dot dot dot. Now usually we wouldn't be using so many terms for answering our questions in exams, but in this lesson I want to use the number of terms that we have here, and we're going to hop over to an online tool to show you, okay, with illustration, the effects of the number of terms and how it affects an approximation. Okay, so if you were to shorten this, and let's say we were to take these out, okay, all the ones from x to the power 5 and above, you realize that the approximation will only work for smaller numbers, okay, smaller values of x. Why is that so? It'll become very clear and apparent when we look at the graphs. Okay, so what we're gonna do is that we're gonna take an online tool, and then we're gonna plot out sine x, and then after that we are also gonna compare, okay, the graphs when we have a different number of terms over here. So we'll start progressively by showing the graph, okay, with x, and then after that the next graph with x cubed over 3 factorial. So we'll just consistently add on to a new term, add an additional term. Okay, so let's move forward over here, and we take a look at how sine graphs looks like. Now I'm using an online tool. Okay, so this is actually very handy. It's desmos.com/calculator. Okay, I like this a lot, so I am gonna use this to illustrate what we're gonna learn about today in this lesson. So I'm gonna go ahead and type in sine x. Okay, so as you can see, immediately once I finish the formula, it shows me the graph. Okay, so we're gonna expand this a little bit. Okay, we're just gonna look at just the graphs over here. Okay, from say -4 to 4. Okay, this is good enough. All right, now we know that according to our Maclaurin expansion for sine x, it is actually x, okay, for the first term, right? So suppose if I were to type x, which is y equals to x, you can see the blue color line there overlapping with our original sine curve. What happens is you will notice that the graphs will overlap, okay, for very small values of x. Okay, that is somewhere I would say between -0.5 to 0.5. So in fact, if you were to just use the first term of the Maclaurin expansion for sine x to estimate the value of sine x, right, you could simply just use x for the estimation if the value is very small. For example, you can key this in, right? So remember to switch to radian mode. So if you key this sine 0.1, which is actually a very small number, you will get 0.0998, okay? And which is actually very close to 1, okay? Right? And then when you use 0.2, you could key in sine 0.2, okay? All right? And then again, you'll get 0.1986, okay? Which is actually very close to 0.2, okay? Which is the original value. Now, can we actually make this a little bit more accurate and also allow us to encompass larger values of x? And that is a resounding yes. Okay, what we'll do is that we'll now go ahead and key in the second term, which is minus x cubed over 3 factorial. So we are going to key that in, okay, in the same graph. So let's go ahead and update this. So we have x, okay, then to the power of 3, divide by, oops, go over like this, and then divide over, okay, so 3, and then an exclamation mark. There you go. So now you see that the graph in blue has been updated. It's no longer a straight line. It's actually more of a x cubed curve. Okay, as you can see over here, more parts of the blue curve and the red curves intersect. Okay, so in this case, the approximation is better. Okay, we have a wider range. Instead of somewhere between minus 0.5 to 0.5 in the previous example, we can now take a value somewhere between, I would say, minus 1 to 1. Okay, it's going to be a very good approximation. So again, let's say we were to key in sine, okay, 0.8, all right, sine 0.8. So sine, you can use a calculator and do this exercise over here. Just go ahead and press in sine 0.8. Make sure you are in radian mode. And then when you press equal, you are going to get 0.717356. Okay, blah, blah, blah. All right. Now, what's going to happen next is that I want you to go ahead and key in using the x minus x cubed over 3 factorial. We're going to replace that with 0.8 for the values of x. So we have 0.8 minus 0.8 cube, okay, over 3 factorial. Now, if you press your calculator, it's going to give you 0.71466, okay, which is actually very close to 0.71735 that we have just now. All right, so this is actually a very good approximation. It's not exactly equal, okay, but very good approximation. Now, as we increase the terms, you will realize that not only the approximation is going to be closer or more accurate, the range of values of x, okay, that we can use will also become larger, right? So it was minus 0.5 to 0.5, then minus 1 to 1. Okay, so let's take a look. What if we were to increase this, okay, to with the third term, which is x to the power of 5, x to the power of 5, okay, over 5 factorial, over 5 factorial. Okay, so again, you see that the graph has shifted, or rather changed, the blue color ones, and now more of the red and the blue curves are intersecting. Okay, so you can see that with 3 terms is an even better approximation. Now, what I'm going to do is this, okay, and for better reference, I'm going to write this down over here. Okay, remember that when we chose 0.8, right, as our x value, and the actual value when we key in sine 0.8, okay, in radian mode would be, let's recall that, okay, 0.71736, okay, if I put it to phi SF, right? And then when we had the approximated value, okay, the approximated value, what happens was when we were using x minus x cubed over 3 factorial, okay, let's recall that we had 0.71467 to 5 SF. Now, let's move forward and say that we use this x cubed 3 factorial plus x to the power of 5 over 5 factorial. Okay, let's take a look. If we were to use x as 0.8 again, what happens? So we plus 0.8 to the power of 5, okay, over 5 factorial. Okay, now what we're going to get is 0.71739, which is 7.7140. Okay, as you can see, all right, compared to the actual value in phi SF, we are getting closer. Okay, so we can do one more just to see the trend. Okay, so that will be x minus x cubed over 3 factorial plus x to the power of 5 over 5 factorial, okay, minus x to the power 7 over 7 factorial, okay? So let's go to our calculator and go ahead and add that term, or rather subtract that term. So we have minus x, which is 0.8 to the power of 7, okay, over the power 7, okay, over 7 factorial, okay, and what we have over here is 0.717355, which rounds off the 36, okay? So now I hope you can see, all right, the effects of the number of terms on the series expansion and its approximation to the actual value. So the more terms you have, the more accurate the approximation, okay? And the more terms you have, all right, it also allows you to have higher values of x, because it would be more accurate, okay? So let's just pop back to the graph. We can see that with just 3 terms, we are able to approximate, value somewhere, I would say maybe around minus 1.6 to 1.6, okay? All right, they coincide very nicely. All right, now let's just add the other one. I think some of you will be interested to see what happens when we add the additional term, which is the x to the power 7 term. Okay, let's go ahead and do that. Okay, x to the power 7 divide by 7 factorial. Voila. Okay, so now you see that more parts of the blue is coinciding with more parts of the reds. Okay, so as we continue to add more terms, the blue curve, okay, which is the approximating curve, will look more and more like the actual curve, which is the sin x curve, the red one, all right? So I hope by using this online tool for illustration, it is clear to you now how the terms will affect your approximation, as well as the range of values of x that you can use to approximate. Okay, now before I end off, I know that some of the students might ask, what if I were to use a value that is out of out of where the blue and the red curves intersect? Okay, what happens is, let's say suppose you were to use 4 in this case, okay, and you press in sine 4, you realize that okay, we're gonna mark that with y equals to 4. Sorry, no, not this, x equals to 4. Okay, so what happens over here is that if you were to figure out, okay, what is the value of sine 4, okay, the exact value, it is actually going to give you to 3 significant figures minus 757. Whereas if you key in 4, okay, replace x equals to 4 with the formula over here, okay, which is the blue color one, you will have minus 1.384. As you can see, it is not a good approximation, okay, because the values are too large, and the reason why is because the curves do not match, okay, at those values of x, or the range of values of x in those places, okay. So that's the reason why when we are doing approximation with the less number of terms, okay, we will want to use very small values of x, which brings us to our next lesson on small angle approximation.